In the early months of 1945, the waters off Japan's coast witnessed a moment that would reshape military understanding forever. An American F4U Corsair, its engine failing during combat operations, plummeted toward the cold Pacific. The pilot ejected as his fighters struck the waves, leaving behind floating wreckage that would soon become one of the war's most significant intelligence prizes. Within hours, Japanese patrol boats converged on the crash site. What they recovered would offer unprecedented insight into American aviation technology during the war's final, desperate months. For nearly 3 years, Japanese pilots had encountered this formidable American fighter across the Pacific theater, over the Solomon Islands, Rabaul, the Philippines, and now above the home islands themselves. They had learned to respect its blistering speed, devastating firepower, and seemingly indestructible construction. Yet never before had they possessed an intact example to examine in detail, to measure with precision, to test thoroughly, and to understand just how far behind their own technology had fallen. The story of Japan's encounter with the F4U Corsair transcends the simple tale of a captured aircraft. It chronicles a nation's technological awakening, the sobering moment when Japan's finest aviation specialists confronted the full magnitude of American industrial and engineering superiority. Through their meticulous examination of this fighter, they would discover devastating truths about manufacturing precision, material science, and design philosophy that would shatter long-held assumptions about their own capabilities. The Corsair that Japanese salvage crews hauled from the Pacific represented the pinnacle of American fighter development. Originally designed in 1938 to meet the United States Navy's demanding specifications, the F4U had evolved from a radical concept into one of the war's most feared combat aircraft. Its distinctive inverted gull-wing design, massive Pratt & Whitney R2800 double Wasp engine, and revolutionary performance characteristics made it instantly recognizable to friend and foe alike. More importantly, the Corsair had achieved something Japanese aviation desperately struggled to match: a perfect balance between speed, firepower, range, and structural strength. The Corsair's genesis dated to 1938, when the Navy's Bureau of Aeronautics issued a revolutionary request for a fighter capable of exceeding 400 miles per hour in level flight. This specification alone was extraordinary. At the time, most fighter aircraft struggled to reach 350 miles per hour, making the Navy's demands seem almost impossible. But the Navy wanted more than just speed. They demanded a complete package. The new fighter needed low stalling speeds for safe carrier operations, a range of 1,000 miles, heavy armament, and the ability to carry bombs for ground attack missions. Chance Vought Corporation's response was nothing short of audacious. Chief designer Rex Beisel and his innovative team decided to build their aircraft around the largest, most powerful engine available, the Pratt & Whitney R2800 double Wasp. This massive 18-cylinder, two-row radial engine produced 2,000 horsepower, nearly double that of most contemporary fighters. To harness this immense power, they designed a colossal 13-foot 4-inch diameter propeller, the largest ever fitted to a fighter aircraft. The engineering challenge was immediate and daunting. How could they provide adequate ground clearance for such a massive propeller while maintaining the structural efficiency essential for carrier operations? The solution became Corsair's most distinctive and recognizable feature. Rather than using conventional straight wings, Beisel's team created an ingenious inverted gull wing design. The wings angled sharply downward from the fuselage before leveling out, creating a distinctive M shape when viewed head-on. This innovative configuration allowed for relatively short landing gear while providing the necessary propeller clearance. The anhedral angle, where the wing met the fuselage, also created optimal aerodynamic conditions, significantly minimizing drag and improving overall performance. The prototype XF4U-1 took to the skies on May 29, 1940, piloted by Lyman Bullard, Jr., Vaught's chief test pilot from the factory airfield in Stratford, Connecticut. On October 1, 1940, during a test flight between Stratford and Hartford, the XF4U-1 achieved a groundbreaking ground speed of 405 miles per hour with tailwind assistance, making headlines as the first single-engine American fighter to reach this milestone. The aircraft's actual maximum level flight speed was 378 miles per hour at 23,500 feet, still exceptional performance for 1940, and a clear indication of the Corsair's revolutionary potential. Production F4U-1 Corsairs began reaching operational units in late 1942. Marine Fighter Squadron VMF-124 received the first combat-ready aircraft, deploying to Henderson Field on Guadalcanal on February 12, 1943. The Corsair's combat debut proved inauspicious and sobering. On February 14, 1943, during what became infamously known as the St. Valentine's Day Massacre, Corsairs suffered a disastrous first engagement. 9 American aircraft were lost, including 2 Corsairs, multiple P-38 Lightnings, P-40 Warhawks, and bombers, while Japanese defenders lost only a single Zero fighter. The 9-to-1 loss ratio in Japan's favor was so severe that daylight bombing missions to Bougainville were immediately suspended, pending tactical reassessment. This devastating engagement demonstrated a crucial truth. Superior technology alone could not guarantee victory. Tactics, experience, and proper deployment mattered equally, if not more. However, American pilots adapted with remarkable speed and intelligence. They quickly learned that the Corsair's strengths lay not in traditional dogfighting, but in what became known as boom and zoom tactics. The Corsair could not outturn a Zero in slow-speed maneuvering combat, but it could outdive, outclimb, and outrun any Japanese fighter in existence. Proper tactics meant maintaining speed and altitude advantages, diving on enemy aircraft with devastating effect, firing with overwhelming firepower, and using superior speed to disengage before the enemy could respond effectively. Second Lieutenant Kenneth A. Walsh of VMF-124 became the first Corsair ace on May 13, 1943, mastering these revolutionary tactics and eventually achieving 21 confirmed victories. His success became the template for effective Corsair employment throughout the Pacific Theater.
As the war progressed through 1943 and 1944, the Corsair's fearsome reputation grew exponentially. Marine squadrons operating in the Solomon Islands, flying from hastily constructed coral airstrip bases, exploited the aircraft's remarkable ruggedness to devastating effect. The Corsair proved capable of absorbing battle damage that would have completely destroyed lighter Japanese fighters, returning home with holes that would have been fatal to lesser aircraft. The Corsair's armament was nothing short of formidable. 6 50-caliber Browning machine guns mounted in the wings provided overwhelming firepower that could shred enemy aircraft in seconds. The 4 inboard guns carried 400 rounds each, while the 2 outboard guns carried 375 rounds each, totaling 2,350 rounds of devastating ammunition. Later variants, such as the F4U-1C, replaced the machine guns with 4 20mm cannons for even greater destructive power. However, many experienced pilots preferred the reliability and greater ammunition capacity of the 50-caliber weapons, which had proven themselves in countless combat engagements. The Corsair's versatility extended far beyond pure air-to-air combat. By mid-1944, Corsairs regularly carried extensive external ordnance loads: 1,000-pound bombs on centerline and wing racks, 8 5-inch high-velocity aircraft rockets, HVAR, or napalm canisters for devastating ground attacks. This fighter-bomber capability made the Corsair absolutely invaluable for close air support during amphibious operations across the Pacific. During the brutal Okinawa campaign in 1945, Corsairs flew thousands of ground attack sorties, earning the grateful nickname Angels of Okinawa from infantry units who witnessed their life-saving interventions firsthand. What Japanese pilots encountered in aerial combat told only part of the Corsair's remarkable story. From the cramped cockpit of a Zero or other Japanese fighter, a pilot saw an opponent that was faster, stronger, and more resilient than anything in their arsenal. But understanding the sophisticated engineering and advanced manufacturing techniques behind these overwhelming advantages required physical examination of the aircraft itself. Japan's capability for such critical technical analysis centered on two premier facilities, the Yokosuka Naval Air Technical Arsenal south of Tokyo, and the Army Aviation Technical Research Institute at Tachikawa. These organizations had been systematically examining Allied aircraft throughout the war, recovering examples from battlefields across the vast Pacific theater. Their previous work had provided valuable intelligence about American capabilities, but most captures were severely damaged aircraft or incomplete wrecks salvaged from crash sites. An intact, operational example of a frontline American fighter represented an extraordinary and unprecedented opportunity for comprehensive analysis. The Japanese Navy's Yokosuka facility had been conducting cutting-edge technical research since April 1, 1932, when it was reorganized as the Kegun Kokusho, Naval Air Arsenal. By World War II, Yokosuka employed thousands of skilled engineers, designers, and technicians, representing Japan's finest aviation minds. The arsenal had designed numerous Japanese naval aircraft throughout the war, though actual production was typically contracted to major companies like Aichi, Nakajima, and Mitsubishi. Yokosuka's engineers were experienced professionals who understood aircraft design at the highest levels of technical sophistication.
When the salvaged Corsair arrived at Yokosuka in early 1945, it represented one of the most modern American fighters yet recovered in relatively intact condition. The aircraft had suffered significant water damage during its forced landing, but the basic structure remained fundamentally sound. Recovery teams had worked diligently to prevent complete sinking, and the fighter was carefully transported to Yokosuka's secure technical examination area. Initial assessment focused on determining the overall condition and examining what remained intact. Despite extensive saltwater immersion, much of the Corsair remained structurally sound and accessible for detailed study. The massive Pratt & Whitney engine would require complete disassembly and thorough cleaning, but the airframe structure showed no combat damage, a crucial advantage. This was absolutely critical for accurate assessment. Previous Allied aircraft captures often involved heavily damaged machines, making it extremely difficult to distinguish original design features from battle damage or crash-related destruction. Japanese specialists began with systematic photography and precise measurement of every component. Every dimension was carefully recorded: wingspan of 40 feet 11.7 inches, length of 33 feet 4 inches, height of 15 feet with wings extended, or 16 feet 2.3 inches when wings were folded for carrier storage. The inverted gull wing configuration immediately drew intense attention from the technical team. Japanese designers clearly understood the aerodynamic and structural advantages of this sophisticated design, but they also recognized its extraordinary manufacturing complexity. Creating the compound curves and maintaining precise angles throughout production required sophisticated tooling and quality control systems far beyond what most Japanese factories could achieve reliably at this desperate stage of the war. The precision required was simply staggering. The detailed examination revealed something that particularly surprised the technical team. Despite the Corsair's obviously advanced nature and modern design philosophy, significant portions of its outer wing surfaces were covered with fabric rather than metal, specifically the areas aft of the main wing spar and armament bays. Both upper and lower surfaces used fabric covering, as did all the control surfaces, ailerons, elevators, and rudder. Japanese aviation specialists initially found this design choice puzzling and somewhat archaic. By 1944-1945, most modern fighters used all-metal construction throughout. However, further analysis revealed a sophisticated reality behind this apparent simplicity. The fabric covering was a deliberate and intelligent design choice from the aircraft's 1938-1940 development period. It significantly reduced weight in areas where structural loads were minimal, saving precious aluminum for critical load-bearing components where strength was absolutely essential. The fabric was specially treated material that, when properly applied, provided adequate strength and weatherproofing while weighing significantly less than metal skinning. This represented a mature understanding of optimal resource allocation for maximum performance, a lesson in engineering efficiency that impressed the Japanese analysts. Disassembly of the wing structure revealed construction methods that technical personnel found both deeply impressive and profoundly troubling for Japan's own capabilities. The main wing spar, the critical structural element carrying all flight loads, was a massive forging of exceptional quality that exceeded anything comparable in Japanese fighters. American metallurgy had produced aluminum alloy forgings with strength characteristics that Japanese facilities struggled desperately to match, even under peacetime conditions. The spar's dimensions and load-bearing capacity were simply extraordinary, representing a fundamental difference in industrial capability. This single component illustrated a devastating truth. American industry could consistently produce large, complex forgings with reliable quality, while Japanese manufacturers increasingly relied on built-up structures assembled from smaller, less optimal components, a compromise forced by material shortages and manufacturing limitations.
The wing's internal structure demonstrated similar levels of sophistication that both impressed and alarmed Japanese engineers. Ribs stamped from aluminum sheet showed remarkable precision and consistency that seemed almost machine-like in its perfection. Each rib was virtually identical to the next, indicating manufacturing processes with extraordinarily tight quality control standards. This consistency stood in stark contrast to Japanese aircraft production, which increasingly struggled with quality variations as the war progressed. Individual Japanese aircraft often showed significant variations in component quality, with some parts meeting specifications while others fell short due to material shortages, inexperienced workers, or damaged tooling. Attention turned to the Corsair's impressive armament installation. 6 Browning AN-M2 50-caliber machine guns mounted in the wings represented truly formidable firepower that could destroy enemy aircraft with devastating efficiency. The installation was compact, remarkably reliable, and engineered for field maintenance under combat conditions. What particularly struck Japanese examiners was not merely the firepower itself, but the complete systems integration. Ammunition boxes, feed systems, spent cartridge ejection mechanisms, and charging systems were all precisely engineered to work seamlessly together as a unified whole. Every component complemented the others perfectly. The guns themselves were specimens of precision manufacturing that represented American ordnance production at its absolute peak. The Browning M2 machine gun was a mature design, perfected through decades of continuous development and manufactured by the millions with extraordinary consistency and reliability. Japanese technicians examining these weapons immediately recognized manufacturing techniques and quality standards that their own factories could not consistently achieve even under ideal conditions. The tolerances, surface finishes, and overall build quality were simply superior in every measurable way. The discovery of 150 pounds of strategically placed armor plate protecting the cockpit, plus a 1.5-inch thick bullet-resistant glass panel positioned behind the windscreen, reinforced growing impressions of fundamentally different American design philosophy. Japanese fighters had largely abandoned heavy armor protection early in the war, favoring lighter weight and theoretically better maneuverability. The Zero's spectacular early success had seemed to validate this approach completely, suggesting that speed and agility could substitute for protection. However, as American fighters grew progressively more powerful and better armed throughout the war, the lack of adequate protection became increasingly fatal for Japanese pilots. The Corsair demonstrated conclusively that proper engineering could successfully incorporate substantial protective armor without sacrificing overall performance. made possible by the massive power reserves of the R-2800 engine. That magnificent engine dominated the entire technical examination process. The Pratt & Whitney R-2800 Double Wasp represented American aero engine development at its absolute pinnacle. 18 cylinders arranged in 2 precise rows of 9, displacing 2,800 cubic inches and producing over 2,000 horsepower consistently, this engine was nothing short of a masterpiece of mechanical engineering. Japanese engineers had encountered this engine before in other captured aircraft, but never had they possessed an example in sufficiently good condition for truly thorough analysis and detailed examination. The engine's construction revealed manufacturing capabilities that seemed almost incomprehensible to Japanese observers. Cylinders were precisely machined with tolerances measured in thousandths of an inch, precision the Japanese engine manufacturers struggled desperately to achieve even with their finest equipment. Pistons, connecting rods, and crankshaft components showed surface finishes and dimensional accuracy that represented the cutting edge of American manufacturing technology. The two-stage supercharger system, designed to maintain full power at high altitudes, incorporated complex internal passages and precisely fitted rotating components that defied Japanese manufacturing capabilities. Japanese attempts to develop comparable supercharger systems had largely failed due to fundamental manufacturing limitations and material shortages that plagued their industry throughout the war. Perhaps most impressive of all was the engine's legendary reliability and consistent power output. American radial engines routinely produced their full rated horsepower for hundreds of hours between scheduled overhauls, performance levels that seemed almost magical to Japanese engineers. Japanese engines, even brand new examples fresh from the factory, often failed to achieve their theoretical power ratings and required constant, frequent maintenance to remain operational. The R-2800's consistent, reliable performance came from superior metallurgy, better lubricants, more precise manufacturing processes, and far more sophisticated quality control systems. Examination of systems throughout the aircraft revealed consistent patterns of excellence that painted a disturbing picture of American industrial superiority. The landing gear mechanism was remarkably complex, but precisely manufactured, operating smoothly despite its sophistication. The cockpit instrument panel presented comprehensive arrays of gauges and controls that exceeded anything available in Japanese fighters. Pilots had access to detailed information about every aspect of their aircraft's performance and condition. The fuel system incorporated revolutionary self-sealing tanks using multiple rubber compound layers that automatically swelled when punctured, preventing catastrophic fuel loss, technology that Japanese aircraft almost entirely lacked, making them vulnerable to incendiary ammunition. The electrical system powered extensive equipment through high-quality wiring with proper insulation and logical organization that facilitated maintenance and repair. Perhaps most revealing was the overall quality of materials and manufacturing throughout the entire aircraft. Every component, from major structural elements down to the smallest fasteners, showed consistent, professional quality that spoke to systematic excellence. Aluminum alloys had uniform properties throughout. Steels were properly heat-treated to optimal specifications. Surface finishes were smooth and professional throughout. The aircraft felt substantial and well-made, built to last under the harsh conditions of combat operations. This overall quality stood in increasingly sharp contrast to Japanese aircraft production in 1945. Wartime shortages had forced the increasing use of substitute materials of inferior quality. Aluminum quality had deteriorated significantly as high-grade materials became unavailable. Skilled workers had been conscripted from military service, leaving factories dependent on inexperienced labor. Manufacturing facilities operated under the constant threat of devastating American air raids. Quality control suffered dramatically as production schedules demanded quantity over quality in a desperate attempt to replace combat losses. The examination of the captured Corsair occurred as Japan faced imminent, inevitable defeat. American B-29 superfortresses were systematically destroying Japanese cities in massive firebombing campaigns. The once mighty Imperial Navy had been shattered at the Battle of Leyte Gulf. The Philippines had been completely liberated. Iwo Jima had fallen after horrific fighting, and Okinawa was under savage assault. In this desperate context, the Corsair examination took on profound and somber significance. This was no longer intelligence gathering for future victories that would never come. Instead, it represented a final, honest reckoning with technological reality that could no longer be denied or rationalized away. Japanese engineers at Yokosuka and Tachikawa wrote comprehensive technical reports documenting their sobering findings. These meticulously detailed reports documented precise measurements, described advanced manufacturing techniques, and offered frank assessments of American capabilities that could no longer be dismissed or underestimated. The tone remained professional and objective, but could not hide the devastating implications of what they had discovered. In virtually every category they examined, material science, manufacturing precision, systems integration, quality control, American technology dramatically exceeded Japanese capabilities. The gap was not small or easily bridged. It represented years of intensive industrial development, massive investments in research and advanced tooling, sophisticated supply chains, and abundant resources that Japan simply did not possess and could never hope to match. By war's end in August 1945, evidence suggests that at least 2 Corsairs had been captured by Japanese forces in various states of repair. Historical photographs show captured Corsairs with patched wings and fuselages, indicating that technical personnel made serious attempts to restore at least one aircraft toward fly-in condition. Whether actual flight testing occurred remains historically uncertain, but the extensive repair attempts clearly indicate serious, sustained efforts to make the aircraft operational for comprehensive evaluation. The desire to understand the Corsair's flight characteristics from a pilot's perspective was clearly overwhelming. When American occupation forces arrived at the Yokosuka Naval Air Technical Arsenal in September 1945, they discovered extensive evidence of Japanese technical intelligence efforts that had continued almost until the moment of surrender. Captured Allied aircraft were scattered throughout the facility in various states of examination and disassembly. Technical reports, detailed engineering drawings, and thousands of photographs documented Japanese attempts to understand and reverse engineer Allied technology. American intelligence officers systematically collected these materials, immediately recognizing their significant value for understanding exactly what Japan had learned about American capabilities during the war. The story of the Japanese examination of the F4U Corsair represents far more than mere technical intelligence gathering. It symbolizes the vast, undridgeable gulf that had opened between American and Japanese aviation capabilities by war's end. When the Corsair first entered combat in early 1943, Japanese pilots flying the legendary Zero fighter could still compete effectively through superior tactics, better pilot training, and intimate knowledge of their aircraft's capabilities. By 1945, even the most experienced Japanese pilots flying their most modern aircraft stood virtually no chance against well-flown Corsairs operated by competent American pilots. The Corsair's overwhelming technological advantages, combined with crushing American numerical superiority and consistently better pilot training programs, created impossible odds that no amount of courage or skill could overcome. The Corsair achieved an official kill ratio of 11-to-1 against Japanese aircraft throughout the Pacific War. American pilots flying Corsairs shot down 2,140 Japanese aircraft while losing only 189 Corsairs to enemy action during World War II,
a devastating testament to the aircraft's superiority. These numbers reflected not merely the Corsair's individual technological superiority, but the entire American war machine's overwhelming advantages: superior training programs, advanced logistics systems, crushing production capacity, and cutting-edge technology at every level of military operations. Japanese engineers examining the captured Corsair understood all of this with painful clarity. They could precisely measure the performance gap, systematically analyze the manufacturing differences, and mathematically calculate the resource disparities that made victory impossible. Their detailed reports documenting these findings stand as professional acknowledgments of Japan's ultimately failed attempt to match American industrial might through determination alone. The technical analysis was unflinching in its honesty about Japanese limitations. The Corsair itself enjoyed a remarkably long service life that extended far beyond World War II. It fought effectively in the Korean War from 1950 to 1953, where it proved invaluable in ground attack and close air support roles, even as revolutionary jet fighters began taking over air superiority missions. Various foreign air forces, including France, flew Corsairs in colonial conflicts throughout the 1960s, demonstrating the design's enduring effectiveness and adaptability to different combat environments. Remarkably, the final combat missions flown by Corsairs occurred in July 1969 during the brief Soccer War between Honduras and El Salvador. On July 17, 1969, Honduran Captain Fernando Soto, flying an F4U-5, shot down 3 Salvadoran aircraft, including 2 FG-1D Corsairs. The final combat victories achieved by the type ironically accomplished against other Corsairs. From its revolutionary first flight in 1940 to its final combat missions nearly 30 years later, the Corsair proved itself one aviation history's most successful and longest-lived fighter designs. For Japan, the encounter with the Corsair formed part of a larger, more profound reckoning with technological reality during the occupation period. Japanese engineers and scientists who had struggled against severe material shortages and industrial limitations during the war now worked closely with American occupation authorities to systematically rebuild Japanese industry from the ground up.
Lessons learned from examining American technology, including the detailed Corsair analysis, significantly influenced post-war Japanese manufacturing philosophy. The emphasis on quality, precision manufacturing, and continuous improvement that characterizes modern Japanese industry has deep roots in the hard lessons learned when Japanese engineers first examined what American industry could produce when given adequate resources and time. The Corsair, recovered in early 1945, represented far more than a downed fighter aircraft. It served as tangible evidence of engineering excellence and manufacturing sophistication the Japanese aviation had been desperately seeking throughout the war. The comprehensive lessons it taught came far too late to change the war's inevitable outcome, but they helped shape the peace that followed and Japan's industrial renaissance. In examining this remarkable American fighter, Japanese engineers confronted the full magnitude of the technological and industrial challenge Japan had faced from the beginning. They had fought with extraordinary courage and exceptional skill. But courage and skill alone could not overcome the massive technological and industrial advantages their opponent possessed. The story concludes not with triumph, but with professional acknowledgement and hard-won wisdom. Japanese technical reports on the Corsair, discovered by American occupation forces and now resting in military archives, serve as silent witnesses to a crucial moment when one nation's engineers honestly confronted another nation's superior capabilities. The specific Corsair they so meticulously examined has long since vanished, likely scrapped during the chaotic post-war reconstruction period. But its profound legacy remains embedded in the invaluable lessons it taught about what technology, properly applied with adequate resources and sophisticated manufacturing capabilities, could achieve. Japanese aviation would indeed rise again in the post-war era, eventually becoming a world leader in aerospace technology. But never again would Japanese engineers underestimate what their American counterparts could accomplish when given the industrial capacity, scientific knowledge, and abundant resources necessary to fully realize their ambitious designs. The examination of the F4U Corsair by Japanese technical personnel in 1945 stands as a watershed moment in aviation history. The precise point when Japan's aviation establishment fully grasped the technological chasm that had opened during the war years. It was a lesson written not in propaganda or exaggerated combat reports, but in aluminum alloys, precision forgings, and manufacturing tolerances that spoke more eloquently than any words could about the true nature of American industrial power.